All right. So, and then you have throttle valves. And remember, these are just classifications. All right. So throttle valves may be partially open to control or throttle flow. All right, and then you have check valves. Check valves only permit flow in one direction only, and open when upstream pressure is greater than the downstream. Closed when downstream pressure is higher. All right. Again, you can have like a check valve in a spot where if you have a tank here and you have a pump that's sitting on the edge of the tank, pumping upstream and trying to go, let's say upstairs, go to the second floor. You would utilize a check valve here because if this pump is operating on when there's fluid inside of it, what's going to happen between this spot here and this spot here? When the pump turns off, all of this fluid that's in this pipe, if this check valve wasn't there, would return back into the pump, and the pump would turn back on because now there's fluid inside the pump, and then it would pump the fluid back up until it ran out of fluid, and then there's no more fluid, so the pump turns off, and it just keeps cycling like that. That's why you would want to have a check valve in this instance, because the pump turns on, it pumps up, it goes past the check valve. Once the pump turns off, the upward flow going through it stops, so the check valve closes. Now all the fluid that is on top of it is keeping the check valve closed, and that pump won't just continuously cycle. And that's a really good instance of why a check valve is needed. And then we have stop check valves, and they act as a stop valve when closed and a check valve when fully open, may be throttled to control flow. All right. Then we have regulating valves. They automatically control the flow at one location in the system in response to a signal. That signal can be flow, temperature, pressure, level, from a portion of the system or from a different system. All right. That could include pressure regulating valves or back pressure regulating valves. So what does it mean that it's in a different portion of the system or a different system entirely? When can you have another system controlling a regulating valve? If we're not dependent on flow, temperature, or pressure, or level, what would another system be dependent on?
Pressure.
Could be pressure. But what about another system that we would want to control?
Direction?
Second?
Direction or no?
Direction? So like the direction of the flow? Doesn't even have to be shipboard related. When would you want to have control from one system to another system? When would they be dependent on each other? Was that? Here, try holding your space bar down when you're talking. Oh,
I guess a boiler and a heating system or something.
a boiler and a heating system. So the boiler would be like the primary. You're on the right track because that's kind of what the example I was going to use. So how about this? Here's one. You have your so that's a pool. All right, that's my very well drawn pool. All right, and there's two things. You can have, some people have this. So this is a propane heater. All right. And this is just going to recirculate water through it. Obviously, there's going to be a filter and all that stuff, but that doesn't matter. But this will use flames from the and burn the propane and heat the pool water. But that's one system. But if you have another system where if you have like a solar heater, where you have basically black tubing on the top of your roof or somewhere on your yard, and that could be thought of like almost like a preheater, that could be a different system. All right. And then you have a valve here. And what you would be regulating is you would be using almost free energy from the sun. But this system is regulating this system. The temperature coming out of this piece of solar heating that you're getting is going to regulate how much this propane heater comes on and off now. All right. Does that make sense to you guys?
Yes.
Yeah, like little, like.
And that's just one aspect of with regulating valves. You can use a regulating valve right here. All right. And how much of water you want to be mixing into it, or if it's not a sunny day and you know you're not actually going to get anything out of it. You can have like a photocell or some sort of light sensor. All right. That will make this regulating valve open or close. Really, we can get as complicated as we want in that system. Most people will just use the regular old valves they can control. All right. Then you have relief valves. Relief valves automatically open at a predetermined level above the normal operating pressure to protect the system. All right. Then you have safety valves. Safety valves are similar in relief valves, but they reset at a pressure below. So a relief valve, if you have a relief valve in the system and it pops at 100 PSI, that means at 100 PSI, that valve is going to open and it's going to release, let's say it's an air tank, it's going to release air into the atmosphere. All right. And in doing so, it's going to basically relieve some pressure. Okay, now it's great. It's now no longer at 100. It's going to drop and it's going to go to now 99. That relief valve is going to close because it's no longer at 100. But a few seconds later, because we haven't fixed the actual problem, it's just going to pop again because now it's going to go up to 100. And that's why you're going to hear almost what it's called chatter. You're going to hear a relief valve going to be popping, opening and closing because it's sitting right at that level that it's going to pop. All right. A safety valve instead it's going to pop still at 100 psi, but instead of closing at 99, it's going to close at, let's say, 90. So instead it's going to open and it's going to stay open from 100, and it's going to drop the pressure all the way down to 90 psi. And then once it's at 90 psi, then it closes. But if the air pressure starts to go up again, it's not going to pop at 90. It's going to only pop at 100. And then it'll drop down to 90. So you're not going to have that chatter. All right. So let's talk about gate valves. So these are classified as stop valves. They either are fully open or fully closed. All right. As far as some terminology is what they go, you have your hand wheel, you have your stem, you have your disc. This is your disc right here. All right, I know it's kind of hard to see. And then you also have your seat. And this is your seat. It goes all the way around it. All right. Now, the big thing about the seat is that it's actually going to be indented a little bit. You can kind of see it in the picture on this side over here, and then you can see it over here on this picture. Both of these are indented, so that way the disc can push all the way down into it. And once it's in, that's going to give your actual sealing, your metal-to-metal sealing that you have right there. So now you have 3 surfaces mating together instead of just one flat. All right? Because if the disc were to just sit properly on the seat like that, one side could be pressed down where the other can be popped open a little bit, and that's not going to make a seal. Now you have the body, the bonnet, and the yoke. All right. Now, why again does this stop valve only do open or close? Why are they not a half? Why can't you throttle with them?
Can you repeat that? Never mind.
Well, repeat which part? So why does a stop valve only function as a wide open or a fully closed valve? Why can't you throttle with it? Why would you not want to throttle with it?
Throttled with it. It just kind of seems.
What would happen if you were to keep it? You see how it's in the position right now on the picture? And you were having flow going through there? What would happen?
Gonna break.
Would it break? It's not going to necessarily break, but it will slightly.
Wouldn't it blow out the seat?
So it would not only, one, it would wear down the seat, but it would, that's very minuscule. What it will really wear down is the disc. All right. Because if you think about it, the seat's going to be, if it's wide open, the seat's still going to be getting worn down. All right. The problem is when you have the disc. All right. When it's fully open, that disc is going to be all the way up in this cavity here. It's not going to be getting affected. But let's say this is the bottom of the disc, the thing that I just drew here. All right. So when water pressure is coming straight at it, and it couldn't, you know, think about it, this could be brine, so it could be a heavily salted, dense. It could be like when I worked on dredging, it could be a mixture of sand and water going through it. And basically that just increases the erosion. And slowly but surely, it will erode the bottom part of this disc, because as water pressure hits it, so as water pressure hits it and goes underneath it and around, because it's going to fill the whole cavity, it's going to hit it and slowly erode some of the metal. Now, instead of having a nice disc where all three contacts are going to be hitting onto the seat, you might end up with something that looks like this, or even smaller, rounded. And now, like we talked about, instead of the disc actually making contact and being flush on all three sides with the seat, the disc will be sitting inside of the same seat, but now it's only making contact on a very small rounded edge right here. And that's not going to make a very good seal. All right. And that's why you don't want to use these gate valves as a throttle valve. You can, but only in one particular instance can you use gate valves as a throttle valve. When would that be?
Would it be for fuel?
It can be for any system.
Could
But
be
it's-
like an emergency,
Say again?
like straight up like only typical like in an emergency. I can only imagine.
Well, yeah, in
Sure.
an emergency, anything goes. But it all comes down to valve arrangement. All right. So if you have two gate valves in series with each other, before it goes off to, like, let's just whatever, a system. All right. And this is coming from a pump. All right. And both these valves right here are gate valves. When they're in line with each other like this, that's when you can use them, one of them as a throttle, but only one of them can be the throttle valve. All right. This one will be the throttle valve, and this one will be the stop valve. All right. So the stop valve will stay as the isolation valve. It will be always fully open or fully closed. You still get that seal. All right. The disc stays protected, and it'll be up in this nice little area. And the throttle valve will be throttled. It doesn't matter if it seals ever again, because you have a sealing valve. You have a stop valve. All right. And the reason I bring this up is there is an instance you'll see this up on the TSES. All right. So that's gate valves. Oh, and one last thing, that's the packing gland. All right. So before we move forward, what's the point of the packing gland? Is it just the name? Because that whole piece right there is the packing gland. All right. So the packing gland in and of itself is just an area where the whole stem is sealed. All right. Because if this gate valve is open, there's all this fluid in here, and the fluid will come up and go in between the stem and the bonnet, and it will leak out. All right. And the point of the packing gland, it's basically the string-like material. All right. And you have a downward view looking at the valve. So you're looking straight down on it. All right. So that's the stem. All right. And then the packing gland's around it here. And basically what you do is you have these little pieces of rope, and they're called packing. It's called packing material. And you put them inside and surround it around the stem and the packing gland. And the packing gland will put pressure down on top of it, and it's squeezing it. So that way it goes and it fills the cavity between the packing gland and the stem, and now it's creating a seal. So now you're not going to have fluid escaping out of it. So in case you do have fuel, or if it's lube oil, you don't want that just going everywhere. All right. So that's the point of the packing gland. All right. Any questions before we move on? Okay. So here's the gate valve. Again, the disc travel is greater or equal to the diameter of the disc. And then it has little resistance to flow when opened. All right. Let's talk about ball valves. So ball valves, stop valve, or stop valve. All right. They function closed or wide open. They have a couple of parts. They have a stem, handle, a packing gland, and a body. All right, suitable for high pressure liquid systems, saltwater valves on submarines. All right, now the reason it's called a ball valve is because the inside here, and the other one was called a gate valve because it kind of looks like a gate going up and down, but a ball valve operates, and the main principles is that it's actually physically a ball on the inside that's hollowed out in the middle. All right. So this whole area is basically a physical ball, like I said, with a hollow out center. All right. So let's get a better. So what's happening here is fluid will flow through the hollowed out center. But when the ball valve is turned 90 degrees, that fluid is not going to be able to move through it because instead of having the hollowed out center to go through, it's going to be blocked by a solid wall. All right. And that's the biggest thing about these things. They're quite literally a ball in the middle with a hollowed out center. And when you turn the handle, it's allowing the flow to go through the middle of it. And the only way you can tell these things are open or closed or is by the one, if you have flow, but you're never going to be able to see inside of a clear piece of pipe, is by the handle. And now we have the butterfly valve. Somebody raised their hand. What's going on? Somebody have a question or? No? Oh, we're in the chat. Okay.
So butterfly valves, they work as both stop and throttle.
Yeah, let me get to this question that just came up in the chat, and we'll get to that next. All right. So why can't it be used as a throttle valve? It's the ball valve. Yes, Mike. All right. So ball valves you can use, like, honestly, everything here you can use it. It's just one of those things where gate valves will have damage to them, so you have to have them in series. And a ball valve can also have damage done to it. All right. They won't really throttle that great because if you have them open, let's say that's the position, which is halfway. What you're going to be having is the ball is going to be focused here and here. So now you have a wall here that the flow is going to be hitting. And this pointed edge right there will start to round off. Oops. And as it starts to round off, you're going to basically give it area to when it's fully open or when you need it to be fully closed. Again, it's not going to make the proper seal. All right, you can either have, and remember, it's not just a 2D shape. All right, it's a circle here, so you're going to be having that problem all the way around it. All right, not just in that one corner. And that rounding can allow leakage to either get by and go around, or it could leak up through the handle. All right. And that's what's can be basically happening with these things. And they don't really throttle that well. All right. So butterfly valves, they could be either a stop valve or a throttle function. So they're pretty simple. They have a body, they have a seat, the disc, handle, and the stem. All right. The seat here is made of like a rubber gasket material. It's harder than normal, like what you would use for like as far as gaskets, because they have to have a resistance back to the disc. All right. Because what's physically happening here is, as you can see in this animation right here, is this piece right here is the seat, these little orange pieces. All right. And as you can see with it, they are squished up against it right now. So when you have this thing closed, this side of the seat is pushing up against right here. And then the same is true on the opposite side. All right, so they're opposed on opposite sides of each other, and that opposition is keeping the valve sealed. And they kind of go past it a little bit. You could see it's actually touching all the way to the edge of the body here. All right, so a little bit of wear isn't the worst thing, and it's not really going to get that much wear done to it. All right. So when they open, and if they're in a throttle position where they're like this, that wear isn't going to matter too much. Because if it starts to wear off, it's just going to seal here. And it's the pressure from the disc to the seat that's going to be sealing it. All right. That's what the seal is. So you can change out these rubber pieces, but most people will actually just replace these butterfly valves because they're so easy to replace, relatively. That's why these things can be used as throttle valves. All right. Glow valves. These things, again, are stop valves or throttle function. All right, you have the seat, the disc, the stem, the hand wheel, the body, the bonnet, and the packing gland. All right. These things are, you'll see them a lot. All right, and a lot more than what you think you really would. All right. These are what are used on hose spigots. All right. Unless you have a hose spigot that's like one of those anti-frost ones, then you don't. These things are used in a lot more of older ships, and they're being kind of phased out into turned into the butterfly valves because they take up less space. But these are fantastic valves for what they are, because all the flow comes up around underneath them. All right. And they can easily be repaired. That's what makes these valves so great. You could take this entire valve apart, this whole top piece here, and you could just take it right off. All right. And what you're exposing is you'll expose the seat on either side. And if you're not getting as much sealant, what you can do is you can just come in there with like a file, or they make specialty grinding pieces that will grind this down ever so slightly and make a new mating surface. And you can replace these discs really easily, or same thing, you put a file to it. All right. And you create a new mating surface, and all of a sudden you have a brand new flat seal right here, and the valve is now fully sealed again. These things are full. That's what makes, like I said, glow valves so great. And that's why they're quite literally everywhere on older vessels, because you could just rebuild them with very simple hand tools. All right. So basically what it's saying here of all this math is that the valve is fully open when this area equals the inlet area. All right. So you don't have to continuously open this valve all the way until the disc is flat up here. As long as the area of flow is equal to the flow coming in, then it's fully open. All right. So these things can be put in a number of arrangements. All right. They don't just have to be in line. They can be a 90 degree, which is right here. They can be straight up and down. They can be sideways. They can really run in any direction. All right. So before we go into swing check valves, anybody have any questions or going at a good pace?
Yep.
All right. So swing checks. Swing checks, basically, they operate off of the idea that whatever is right here, this piece, is heavier and will close with no flow. All right. So this naturally wants to be closed. All right. So the flow is going to go through and it's going to push this up. But as soon as the flow pressure stops, that swing check wants to close. All right. It's all based on the weight. And it's the weight of this piece. All right. And what's great about it is they can be mounted horizontally or vertically because gravity is still going to affect them the same. All right. Whereas with a lift check, can only be mounted horizontally. And that's because this is pushing up on a disc, and this disc is only going to be able to function up or down this way. If it was mounted horizontally and that disc went up halfway, there's no reason for it to come back down or to go back sideways, because the gravity is going to be affecting it. All the force is going to be applied here, not where you want it, which is up and down. All right. So stop check valves. They function as stop valves, and when they're open, they function like a check valve. And the reason for that is because these two pieces are not physically attached to each other. They're connected in the sense that this piece, this stem right here, will never go far enough away that this seat, this piece right here, will never become detached from it. All right. You'll never get to the point where it comes out of the stem so far that this will move, and now it will never become realigned. All right. The stem will always be the guide for the disc. All right. So when it's in this position, what's great about these things is you can use them as throttle valves. All right. But you can use them as throttle valves only when there's pressure. So if you have something that's, you're operating a fuel pump, and you turn on your fuel pump and it's going through and it's sending fuel to whatever tank you want it to go, and it's pumping fuel, and this valve is open. As soon as there's pressure, this disc is going to lift up. But now, say if you have a fuel pump failure and the pump shuts off, you don't want whatever is in your tank to backflow. So since there's no longer pressure pushing this disc up, it shuts closed, and now all the back pressure is keeping that disc from opening. That's what makes these valves so great. All right, and then they can be used to throttle as well. All right. So let's just talk about some nomenclature with valves. We have our isolating valves. All right. We have our suction and our discharge, and we have our inlet and outlet. And both of these are isolating valves. They are isolating a piece of equipment. All right. This inlet and this outlet are only inlet outlets in relation to the fuel oil heater. And this suction and this discharge are only suction and discharges in relation to this pump. All right. And their names are all in relation to what, like I said, to the pump or to a fuel heater. If it's a piece of equipment, it's an inlet and an outlet. So if it's the inlet to a turbine, that's, like I said, the inlet. It's not going to be the suction to a turbine. That doesn't make any sense. All right, where are you taking suction from? That would be like a tank. All right. Now, you have root valves. And root valves are basically what's protecting the burner valve. All right, same thing again. If you were to be throttling with your burner valve or anything like that, these root valves are going to be isolating that part of the system. All right. So, and then you have control valves, and they're constant pressure regulator. All right. So this is the control valve in that scenario because it's taking a signal from the downward line, and that signal is pressure. All right. Or it could be a temperature. It could be flow, but in this instance, it's a pressure regulator. All right. So it's 10 a.m. Do you guys, before we start getting into regulating valves, do you want to take like a 10, 15-minute break?
Uh,
Or you want to keep going? It's up to you guys.
fine with the break.
Break.
Break for 15 minutes?
yeah.
Yeah.
All right, so let's just call it 10, 15. We'll start making our way back, all right?
Okay.
All right. Everyone back?
I'm back.
All right. Yeah, if you guys are feeling it, let me know. All right. You guys are getting a little, it's getting a little rough or whatever, or want to take an extra break, give me a heads up. All right. So let's talk about regulating valves. All right. And here's the big thing that we have to talk about with these things. Like I said, in the spring semester, these things operate, and you can always decipher these things just by looking at them. All right, and this is a pressure regulating valve. It's maintaining the downstream pressure. All right, and just how we were talking about inlet and outlet, and it's how it's relation. When you talk about downstream or upstream, it's all talking about in relation to what? And then the relation is to the valve itself. All right, so downstream is in the direction it's flowing. All right. So it's regulating pressure is the closing force here. And the spring is the opening force. And the way that's working here is you have like this baffle material right there. It's like a piece of rubber. All right. And the piece of rubber is going to be sealed on the outside edge. And then you're going to have almost like a piece of brass in the middle where the spring is going to be putting the force down on it. All right. But this piece of rubber here that's all in the middle is allowing flexibility. And that flexibility is because this pressure that's here is going to be the same pressure that's inside that gap. All right. This is all going to fill. Come on, you stupid thing. Let's just say it's water. All right. Now, this area below is going to fill with 50 psi of water. All right, that's on one side of the baffle. And on the other side, it's just air. All right. But that air pressure really doesn't matter. That's just atmosphere. But what really matters there, and that's the counter force, is that spring. All right. Let's get some more room here. That spring is what's regulating the pressure. All right. That spring is attached to the top of the baffle, this piece right here. All right. And that baffle is going to be attached to the valve. All right. And then just as shown in the picture, that spring can go up and down with this thread here, this nut. So what's happening is that you have 50 PSI, let's say 50 PSI of water coming in, and we're trying to regulate how much pressure is downstream of it. All right. So this spring is going to regulate that. So if we want more than 50 PSI, would this be the proper setup for that?
No. Like,
Why not?
is the when the spring not be able to handle that, or or maybe we just be too much regulation with that spring?
Let's say the spring can handle it.
Okay.
So what's going on here if we look at it? We have the spring that's pushing downwards, right?
Mhm.
So the spring is going to be regulating it. But the other thing we have to look at is which way is the seat facing. So it's seating upwards. So it's pushing up.
Okay.
All right. So if the seat is pushing up, it means that whatever is downstream, if that becomes too great, it will overcome the spring pressure and it will close the valve. Okay?
Yeah.
That's what we have to look at right here. Whoop, that wasn't supposed to happen. That's what we have to look at. Is as this fluid goes through, this pressure down here, if it overcomes the spring force, it will close the valve because it will push up on that baffle. All right. So this would not be this would not be if we wanted to regulate a higher pressure than 50 PSI, let's say. All right. So this would be regulating a certain pressure that this spring is going to be tensioned to. All right. This will be set for a certain pressure. So that way, if you, let's keep it with it. We want 50 PSI. So if we're at, let's say 40 down here, that's our right now. So we want 50 PSI. What is going to happen? What's happening inside of this piece right there?
So with 40 PSI is what you're asking, right? With 40, what's happening?
Yeah, we want 50, but we have 40. What's physically happening inside of here?
So the spring is holding the valve open right now,
Yes.
correct? 50 would close it.
Yes.
That what's happening in there, or
Yep. So what's the conditions inside?
the spring is overcoming the regulating pressure, I guess.
Exactly.
Yeah.
So the spring is the opening force and the regulating pressure is the closing force. So if we want 50 PSI, Once we achieve 50 psi, we have 50 psi. That's what we want. So it's going to be, the regulating pressure is going to be closing the valve.
Have
All right.
40, then the pressure is less, so it opens the valve less, which means that it pushes. I mean, it opens the diaphragm less, which pushes the valve open more, so it lets in more fluid, which raises the pressure up.
Exactly.
Pretty much.
All right. So you have the downstream pressure right here. If it's lower than the set point, and our set point is the 50, that spring is going to overcome that 40 psi, and it's going to open up the valve. All right. And in opening up that valve, we're now going to get more flow going through, and it's going to increase to 50, and it's going to close, and it'll just keep cycling that, and it's all automatic. And you could set it, if you want 75, you increase your spring force. So if you screw down on this spring, you're going to put more tension on that spring. The only way it has to go is down, because you have a force of the nut and the bolt holding it down. And now you can achieve a higher pressure on the downstream. Does that make sense? Does everyone see the steps that we took to decipher how it was going through? We started with how the seat was facing. All right. And where...
Quick question.
Yep.
What do you call, so the 50 psi in this situation, what do we call it? Like we call it the ideal pressure or something, or because that's the level we want to meet, right? What do you call that?
I wouldn't call it the ideal. Call it like the set point. All right. That's the proper term for it. Now, does everyone understand how we did this? We know we started with the seat, and we started with the disc and how it's facing, right? We looked at the spring, where the spring was actuating on, because it could be, we're going to see in the next picture, it's going to be actuating from below. All right, so what side of the diaphragm it's on. And then the last thing is where we're taking our pressure or our fluid flow or what, it could be anything. But what are we regulating? Where is that actuating on? Is it going to be from above? Is it going to be from above and back on the upstream side? Is it going to be from below on the upstream side? Is it going to be from above on the downstream side? So all those four positions, and then the two positions of the spring, either above or below, and then the two positions of how it seats. Either it's seating on top of it or it's seating below it. All right, so those are all the things that we have to be looking out for. So with this one, this is an unloading valve. All right, it's maintaining upstream or back pressure. So it's still seating in the same direction, but the two things are different here. The spring is underneath, and now we have regulating the upstream pressure. All right. And it's coming in on top of that diaphragm. So what's going on there? Let's break it down. So let's keep it the same. We want to keep 50 psi on this side of the system. So we want 50 psi, but let's say we have 60. What's going on? Remember when we talked about hydraulics? 60 psi is here, but 60 psi is also there. So what's going on first?
60 psi is traveling
I lost you.
So up top is 60 psi first, right?
Mm-hmm. But we want to maintain only 50 on back pressure. So what's going on?
It's opening it. If 60 is up top,
What's the first thing we got to look at here? We want 50, and 60 is too high. We're trying to maintain a back pressure of 50. So 60 is too much, and if we had 40, 40 would be too little. We want 50. All right, that's where we set our spring to be at. That's our set point. So if we have 60, that means we have too much back pressure. So naturally, what should we do? We want to relieve that pressure. So how do we relieve that pressure? What's the first thing if you have too much water level, you have too much fluid in a cup? What do you need to do?
Okay. That review I did today on that contract or this morning.
Drain it.
That's got a whole bunch.
You drain some of it. All right. So same thing. If you have too much pressure,
Be really careful. And I'm sure.
how's the best way to get rid of some of that pressure?
open a valve.
Yeah, like open it up.
Exactly. You want to open it up and relieve that pressure. Okay. So that's the first thing we already know. Just in this example, we want 50, we have 60, so we have too much. All right, we have too much of this. We know we have to open up this valve, so that helps us out there. And if we look at this seat, it's going to be opening when it's opposing the spring force. Everyone see that? So the spring force is the closing force. So the spring is going to be set at 50 psi, whereas what's happening inside this pipe is going to be opening up that valve. All right. So if we have 60 psi, 60 psi is going to overcome the set point of this spring is 50 psi. That's the force that's being applied. All right, so 60 is greater than 50 psi. So that is going to, 60 is greater than 50 psi. So that high pressure on top of that baffle is going to push on that spring. It's going to compress that spring. And compressing that spring, it's going to open up this valve and allow fluid to escape. And it's going to go from 60 to 59 to 58 and all the way down to 50. All right. And even at the greater level of 60 psi is going to push that valve open. And it's going to almost wide open it, you can think of. But at 55 psi on the top, it's only going to be half closed. And then at 51, it's going to be just slightly open because 51 is just slightly larger than 60. Than 50. All right. So is everyone getting how to break down these valves? All right. Where to start? If you're ever getting confused on these things, and say we're on a test or in real life when you're looking at these things, set some numbers to it. Start just where the seat. Where's the seat going to be closing? It's going to be opening or closing when you put pressure down on it. All right. and then you look at where is it regulating from. And then finally, you look at the spring. And those 3 pieces of information will tell you everything you need to know about these valves. All right. So, and as we talked about before, we can use air pressure instead of direct regulation coming from the fluid you're regulating. All right. So these are air regulated. So instead of having fuel oil sitting on the top part of these valves, we have just air pressure. All right. This is a downward seating valve, and that's an upward seating valve. So a direct acting would be coming up on top, and indirect acting is coming from below. And now here we have a fuel temperature regulating valve. All right, so the sensor is here, and that is sensing the temperature on the outlet of the fuel heater. All right, that sensing goes into a pilot valve. That pilot valve is going to be transferring that electrical sensor, that temperature sensor, into a pressure signal. That's going to be air. All right. And that air is going to go into our regulating valve. And that will control the outlet of the fuel heater's temperature. All right. Because this is going to be a steam line coming in. So other controls that can be going into these control pilots can be temperature, flow, level, all these different things. All right. So let's just talk about some normally closed valves. We have relief valves. And as you can see, this relief valve is coming back in. It's coming out of the outlet of the pump, and it's going into the inlet of the pump. All right. Remember, we're talking about fuel here. We don't want this thing just going right into the bilge. All right, because that does no one any good, especially the company that paid good money for that fuel. All right. So again, like we talked about earlier, the relief valves open and reset at the same pressure, whereas a safety valve opens at a certain pressure, it goes down to another pressure, and then it will only open at that certain pressure. All right, so it gives you a little bit more room instead of just hearing chattering. And then you have bypass valves. And all bypass valves are is if, certain systems, like if you have a regulating valve that's broken, and then you can regulate it manually while you're trying to work on the valve itself. That's when you would open and regulate these bypass valves yourself while you're, working on these regulating valves. Give me a second. All right. And then we have recirculating valves. And recirculating valves, all they're doing is that you can have the entire system just recirculating and going nowhere. All right. Because if these are all our burners for the boiler, burner 1, 2, 3, and 4, if you're only operating 2 burners, you don't want your pump to be sending, different levels of fluid and everything else like that, and having to, you have to turn on another burner. Now I have to go and increase the speed of the pump, or, you don't want to have to deal with that. And the other thing is that you're always, no matter what, going to be sending the same amount of fluid, the same pressure is needed on burner 1 as it would be on burner 4. They operate at a certain pressure. Okay? So this pump here is going to be constantly putting out the same flow. It's going to be putting out the same pressure. But if you only have 2 burners going, the fluid that would be normally going to 3 and 4 is just going to be recircling back and going right to the beginning of the pump, or it might be going into the tank, and it's just going to be constantly recircling. So that way, if you ever have to turn on burner number 3 or turn on burner number 4, you have the ability to. All you have to do is just open up one of these valves and let your burner off, and you're good to go. All right. So that is it. For valves. All right, it's 10:44. That's really all I had for you guys today. Like I said, tomorrow we have a quiz on valves. All right. The other thing too, I want to make sure you guys are aware, you have to sign that STCW. All right. Someone already sent it to me electronically. They electronically signed it. That works. All right. Get that to me. Well, if you don't have it, if you cannot get it to me and you're having technical issues, we'll figure out a way to get you to sign it. All right. Other than that, I'll see you guys tomorrow. All right. We still have class until noon. So if you guys have any questions, or if you want to stick around and go over anything, I can do that. Other than that, you guys are good to go.
Excuse me.
Yes.
Where do we find the form for the CW class we have to send you?
Okay, so you're going to go to log into Blackboard. Go screen share now. All right, so I'm on the modules page of Blackboard right here. All right. So it's going to see STCW attendance. You'll click on that. All right. And then basically when you download it, what you're going to see is this. All right, you'll get this piece here. And then you'll see this piece down at the bottom. This is what a fillable PDF looks like. All right, so you'll just type in, and then you can go into and sign. All right, so you click up here on the sign. I have my signature already imported. Close that out. That can go there, or you can also sign yourself, where you can come in there, sign it with a mouse. All right. And that's basically all you're going to have to do.